Hello, welcome to Maths with EJD. In this video, I'll be talking about transshipment problem with linear programming. Okay, up till this point, I've been talking about the transportation problem with different approaches, even how to optimize and things like that. So here we're talking about transshipment, which is an extension of transportation problem. But let's see what is unique about transshipment. So the transshipment problem the transshipment problem is an extension of the transportation problem where goods can be transported not only from sources to destinations, but also through intermediate points called transshipment nodes. Transshipment nodes. These nodes can both send and receive goods, which allows for more flexibility in transportation planning. This brings to my mind the idea of courier, So when you send and when you send a message, a parcel, so to speak, from a particular country. So there are many places to get to before it finally gets to the destination. So that's a very good idea of transshipment. So each of the places it gets to before it finally gets to the last destination, you can see those as transshipment nodes. So, but I mean, it's a bit more complicated than what we're talking about here. But this gives us a basic idea of that. So for it allows for more flexibility in transportation planning. So the goal here, just like in transportation problem, is to minimize, we want to minimize the total transportation, costs while ensuring that supply, demand, and intermediate flow flow intermediate flow constraints are satisfied. So that is the goal of transshipment problem. So let's see a particular problem we can solve with this. So imagine that we have three suppliers, okay? Or you can also see them as sources, right? We have three suppliers, and then we have and we have two transshipment nodes, of course, together with what they can supply, what the suppliers can supply, that is. So here, so to move from supplier one to transshipment node one would cost $4. This costs $3, 2, 4, 3, 5. And the supply capacity from supplier one is 30, maybe 30 trucks or 30 whatever, then 20 trucks, 25 trucks, so to speak. And then, of course, since it involves transshipment, we now need to consider the transshipment nodes and how they finally move to the destinations. So we have destination one, destination two, and destination three here. Of course, in this case, we need to know the demands from each of the destinations. So here we have the demand. So, in transportation problem, we have demand and supply on one table. But here, because of transshipment, we need two tables to show that. So the cost to move from transshipment node one to destination one is $2. T1 to D2 is $3. T1 to D3 is $5. And T2 to D1 is $25. Is $7. Then T2 to D2 is $6. T2 to D3 is $4. And the total demand is 25, 25, 25. Okay, now you will discover that supply is equal to demand. Supply is 30 plus 20 plus 25, that's 75. And demand is 25 plus 25 plus 25, which is 75. So this is a balanced, we have a balanced situation. So here we have the case is balanced. If it is not balanced, we need another, we may need to do bits of changes in the way we formulate the linear programming problem. But here we have a balanced situation. If it is, it doesn't have to be balanced. That's basically, it doesn't have to be balanced. So the balanced thing is here and here, but it doesn't have to be. That's what I'm saying. So if it is not, I'll talk about the possibilities we get, in that situation. So let's look at that now. Okay, so we have the table, but again, don't forget the goal is you want to see the cheapest cost. I guess I should have called this example, right? Example. So our goal is want to minimize the cost of moving from the supply nodes to the transshipment nodes to the demand nodes. So let's say now solution. Now with what you have already, right? It's very good if you can have if you have a diagrammatic form of it. So we have three supply nodes. Let me call this okay, we have three supply nodes, right? We have supply. So that is 1, 2, and 3. We have those three supply nodes. Let's call it supply nodes. Then we now have two transshipment nodes. Let me call that 1 and 2 again. So those are transshipment nodes. Transshipment nodes. And lastly, we have three demand nodes. That's 1, 2, 3 again. So these are the demand nodes. Okay, these are the demand nodes. So what happens is that based on the table, right? To ship something from, okay, let me do this. To ship something from supplier one. Okay, I think I also have to do this. Okay, let's do this. Say, so supplier one can supply 30. Supplier two can supply 20. Supplier three can supply 25. That's what we have from the table. Then we have for the demand nodes, right? The first destination is demanding 25. The second, okay, each node is taking 25 basically. Okay, that's what we have. So let's talk about so these are, you can see these are the cost matrices now. So these are the cost matrices. All these 4, 3, 2, 4, and all those you're seeing are the cost matrices. So to ship from 1 to 2, I mean 1 to 1, from supplier 1 to shipment 1, that is $4, right? So we have 4 here. So to ship from 1 to 2, that is $3. So we have $3 like that. Then to ship from 2 to 1, that is $2. From 2 to 1, that is $2. So as you can see, 2 to 1 is $2. Then from 2 to 2, from supplier 2 to shipment node 2, that is actually $4. Then to ship from 3 to 1, from 3 to 1, that is $3. To ship from 3 to 2 is actually $5. So that's about between supplier and shipment node. So now, what if we talk about this? We want to ship from transshipment node 1. So we can ship from transshipment node 1 to demand node 1. And the cost in that case, transshipment node 1 to demand node 1 is 2, right? So we have that's $2 from 1 to 2. From 1 to 2, that is $3. From 1 to 3, that is $5. And we can also ship from 2 to 1. So from okay, I don't want to cover that. So from 2 to 1, let me go this way. From 2 to 1, that is $7. From 2 to 2, from 2 to 2, that is actually $6. And then from 2 to 3, that is $4. Okay. So that's the kind of setup we have for transshipment. So the next thing we need to do is to formulate the linear programming problem. So the linear programming problem, the linear programming problem is formulated as follows. Formulated as follows. Okay. So we have to minimize. So we want to minimize Z equals a lot. Z equals a whole lot. So let's assume that the decision variables here are xij's, whereas here they are yjk. Okay, so from supply to transshipment is xij, from transshipment to demand is yjk. Okay, let's assume that. So if that is the case, it means that we want to minimize Z equals X. So that means X11. So we have 4. Okay, before we even begin to say that, before we begin to do all of that, right? Let's talk about the decision variables. Really important. Okay. So we have Xij. That's Xij. That is number of units shipped, number of units shipped from supply node, I to transshipment node J, to transshipment node J. Okay, that is Xij. Then we can also have yjk. Yjk will be the number of units. Okay, this is number of units shipped from transshipment node J, from transshipment node J to demand node K, demand node K. So that's how that goes. All right, so then we can talk about the objective function now. So of course, these are your, just like these are your decision variables. Decision variables. So talking about the objective function, so we want to minimize z equals 4. So if you move number of goods, some units of goods from supply node 1 to shipment node 1, so that's $4 multiplied by the number you move. That'll be x11, right? So you have 4 times x11 plus the next one, right? You have, that'll be 3 times x12, right? As 3 times x12. So I'll just go. So 3 times x12 plus 2 times x21 plus 4 times x22 plus 3 times x31 plus 5 times x32. Okay, these are the 6 moving from, so that's so this is x11, this is x11, x12, x21, x22, x31, and x32. Okay, multiply by each one like that. So that's what we have that. But that's not done, because we also have to look at, because costs are involved to move from transshipment nodes to the demand nodes. So in that case, we just go ahead and say plus. Now those ones are now the YJKs, right? So now you have so if you look at this now, this is 2, this will be Y11, right? This is Y12, this is Y13, this is Y21, Y22, and Y23 that you're moving. So in that case, we have 2 times Y11 plus 3 times Y12 plus 5 times Y13 plus 7 times 7 times Y21 plus 6 times Y22 plus 4. Sorry, that's Y22, not X22. 6 times Y22 plus 4 times Y23, right? Yeah, 4 times Y23. So that's the objective function. So let's look at the possible constraints now. So if you look at each shipping place, okay, if you look at each supply place, right? This supplier 1 cannot supply more than 30. So that's the limitation already. So whatever is going from 1 to 1 or 1 to 2 cannot exceed 30, or maximum it can be 30, right? Now, since we have a balance in the whole thing, so this is 75 and this is 75, we have a balance. So we can just we can use equality because everything is going to be shipped. But if this side, for instance, was bigger than the other side, then we'll be having less than or equal to here, because it means that the demand side cannot take everything. So we have to ship less from the supply. But if the demand side has something bigger than the supply side, so we are going to have less than or equal to on the constraints for that side. So let's see how that goes. So talking about the supply side now, it means that x11 plus x11 plus x12 has got to be equal to 30. It's equal to 30 because there's a balance in the whole thing, right? But if there was no balance, if the supply side was bigger than the demand side, we'll be having less than or equal to 30. So we have x11 equals 30. Then we have x21 plus x22 equals 20. And then we have x31 plus x32 equals 25. Okay, that's all this now. So x11 plus x12 cannot be more than 30. Then x21 plus x22 cannot be more than 20. Or it should be 20, right? Like because everything is going to be shipped away anyway. So that's why we have that. Then x31 plus x32 cannot be more than 25. So here now we have the what you can call the supply constraints. Supply constraints. Okay. Now, in between this, you can now talk about the transshipment, transshipment, what is it called now? Transshipment balance. Yeah, I think that's the word to use. Now, the idea is that whatever comes into the transshipment node will flow out because it is just a temporary stopgap between the supply and the demand. So it means whatever flows in has to flow out. So it means that X11, X21, and X31 all flow into one, right? But they will go out as Y11, Y12, and Y13. Okay. So in that case, we have to talk about the transshipment balance. So that simply means that x x11, all right, plus x21, that's what is coming from 2 to 1, and then x31, all of this should be equal to whatever flows out. So whatever flows out now would be now y11, okay, plus y12. That's moving from 1 to 2, then y13. So there should be this balance. So if you like, you can actually, move all this to the other side so that you have x11 plus x21 plus x31 minus y11 minus y12 minus y13. So everything is equal to 0 like this. So we can have this. All right. So this is this now. So the next one is that you can also have whatever goes into the second transshipment node also flows out. So we have x12, right? x12 plus x22 plus x32. That is whatever is flowing from each supply node into the transshipment node is also going to flow out in form of y21, right? Plus y22 plus y23. So you can also rearrange and have x12 plus x22 plus x32 minus y21 minus y22 minus y23. All of this will be equal to 0. Okay, we have this now. So this you can consider as the transshipment balance. Transshipment balance. It's a kind of constraint too. You want to see it as a kind of constraint. Now, that's not all. We also have we have the third side, right? So we have got constraint for supply. So we also have demand constraints, right? Each node can take 25. They can't take less than or more than 25 because the demand is exactly 25. But if the demand was higher, overall demand was higher than overall supply, then we'll be having less than constraints. So in this case, we have equality constraint because everything has got to be supplied. And because everything has got to be received also, right? Then it means you're going to have so the supply constraint. So whatever flows into one cannot exceed 25. That means that x at y11 plus y21 plus y11 plus y21. That's all that would be, right? So y11 plus y11 plus y21. Okay. These are the only two things that can flow there, right? Y11 plus y21. Yes, that's all that can go there. Should be equal to 25. In the same way, y2, y12, right? Y12 plus y22. So whatever flows from transshipment node 1 and whatever flows from transshipment node 2 into the second demand node you cannot exceed 25. Then same y3, okay, y13 also, y13 plus y32, whatever flows from uh okay, 1 to 3 and 2 to 3, sorry. Y13 plus y23, right? Should also be 25. So here, this will be your demand constraints. So your demand constraints. Okay, these are your demand constraints. So this cannot exceed, right? So all this cannot be exceeded. Then, of course, we are not done with the constraints. If you remember, we always have non-negativity constraints. So it means that each xij is greater than or equal to 0, and each yjk is also greater than or equal to 0, because we cannot have negative values for the constraint, right? So it means we have non-negativity constraints, non-negativity constraints. Okay. So now that you have formulated the problem, um, you can now solve using simplex method. Of course, graphical method will not be possible here because we have how many several variables. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the number of variables will be like number of the multiplication of the nodes. That's 3 times 2, 6, 6 times 3. Oh, maybe it's even more. 3 times 2 is 6, 6 times 3 is 18. So, but here we have 12. Maybe I think I'm very sure if we settle down, we'll find a formula to know the number of variables you are going to have based on the number of nodes. So I think it will make sense. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 6 plus 6, that's 12. So we have 12 variables. So if you do simplex method, it's going to be really tedious, but we can really do that, right? But to make life easy, I have decided to just use to do to just do use Python code like I've always been doing. So let's go and check for what the Python code looks like for this particular problem. So here we have the Python code. Of course, I always like to use PuLP and linprog. So this is the PuLP code, right? And of course, let me put the line numbers. Yeah, this now. So we have this transshipment problem. Everything is put in. So you have the supply 30, supply 2, 20, supply 3, 25, and the demands, all of that. Then we also have the shipment costs, right? From S1 to T1 is 4, S1 to T2 is 3. We have all that. Then we have also the shipment to destination. All of that is supplied to. Then everything is defined as necessary, and then, if you just go through this, you see how the whole setup looks like. So I'll just run this. And then we have the optimal cost, optimal transportation cost Z is $435 here. And then we see that from destination one, so X11 in short is 5, then X12 is 25, X1, X21 rather. So X21 is 20, X22 is 0, X31 is 25, and X32 is 0. And then, of course, we also have Y. So Y11 is 25, Y 12 is also 25, Y13 is 0, Y21 is 0, then Y22 is 0 again, and Y23 is 25. So that's the answer that PuLP gives us. linprog also gives the same answer. If you look at, of course, the normal setup, give the supply, give the demand, then all the costs you supply, and all the costs from supply to transshipment from transshipment to demand, to destination or demand, right? And then we have all the whole setup like this. So you can just look through this and see how that looks like. So we get exactly the same solution. X11 is 5, X12 is 25, X21 is 20, X22 is 0, X31 is 25, X32, X32 is 0, Y11 is 25, Y12 is 25, Y13 is 0, Y21 is 0, Y22 is 0, Y23 is 25. So the two codes actually give us the same result. So we can say with a level of confidence that that answer is correct, because two different approaches of coding is giving us the same results. So using PuLP, and SciPy dot optimize dot linprog, we obtain the optimal solution. We obtain the optimal solution as follows. Okay, we have x11 is 5, x12 is 25, x21 is 20, then x21 is 20, x22 is 0, x31 is 25, and x32 is 0. Okay, should have managed my space properly, but I mean that's okay. X32 is 0. Then we now have y11 to be 25, y12 is also 25, then y13 is equal to 0, y21 is equal to 0, y22 is 0, and y23 is equal to 25. Okay, so it means from supply, this simply, okay, okay, let me conclude with minimum, okay, with minimum transportation cost, with minimum transportation costs put at $435. Okay, $435. And how to simply get that is just take it back to the objective function, which is really plenty. So you have four times 5, then 3 times 25, and so on and so forth. So you end up getting $435. So it means that from supplier 1, you ship five units to transshipment point 1. From supplier 1, ship 25 to transshipment point 2, and so on and so forth. That's basically what that is about. So there's a lot to learn on this channel. So if you have not subscribed already, you want to do that right away. And you also want to hit the notification bell so you can always get alerted each time a new video is released. Then you want to comment to let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then you want to like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.